Welcome to this class. In the last class, we discussed about the scanning electron microscope, the column, and also the scanning electron image and the backscattered electron image. Now we will just discuss about the detection of these secondary electrons and the backscattered electrons. Okay, you can see in the right side, this is your pole piece, this is your detector. Okay, and exactly at the bottom there will be a sample. Your sample surface. Okay, so this is your inside chamber of the SEM inside chamber. Okay, so in this, for detection, this particular detector is the cross section is shown in this in the left side figure, where you can see that this is your final pole piece, your electron beam interacting with the sample, and the specimen is tilted at a certain angle. And when the electron interacts with the specimen, so it will generate the secondary electrons. And these electrons, when it gets ejected out, usually these secondary electrons will strike a scintillator. Okay, example, it's a phosphor screen. This is your scintillator. Okay, and this phosphor screen, when these secondary electrons strike, it emits light. So here there is a cross section of a scintillator. You can see that the incoming secondary electrons will go and hit to the scintillator, and this scintillator will emits light or photons, and this light is passed through a light pipe, which is or light guide we can tell, and into a photo multiplier. So this section is called a photo multiplier, where the photons are again converted to the pulse of electrons. And this pulse of electrons is nothing but the amplified version of that particular light or the photon. Okay, and secondary electrons, usually they have a very low energy. It is around 50 electron volt, less than 50 electron volt, from 10 electron volt to 50 electron volt, and they have a very low to excite the scintillator. Okay, so that's why what we do is, first is they are accelerated bias voltage. So this bias voltage is around plus 10 electron volt, or it can be a 10 kilo electron volt or 12 kV. Okay, so this is applied. Remember, the sign is the plus, and these are applied to a aluminum, which is a thin film which is covering the scintillator. So this is a aluminum coated on the scintillator, and which has a positive voltage, which is around plus 10 kilo electron volt or up to 12 kilo electron volt. Okay, so now along with this aluminum scintillator, these are actually connected to a Faraday cage, and this Faraday cage is nothing but it's a metal grid. It's a metal grid, and which also called as a collector, and this is kept at a few volts, 200 volts plus 200 volts. Okay, and there is a very important role for this Faraday cage. The first thing is, it prevents the high voltage of scintillator affecting the electron beam, the electrons which are coming towards the scintillator. Okay, and also it improves the collection efficiency by guiding these secondary electrons in towards the scintillator. Okay, so these are the two functions of the metal grid or the Faraday cage. Okay, so this is a detection of secondary electrons. Fine. If in the case of backscattered electrons, they also hit the ET detector. Okay, and these detectors are called Everhart-Thornley detector. And along with the secondary electrons, it might possible that the backscattered electrons also will be hitting to this scintillator. Okay, so the image which is formed from the secondary electrons, with this detector is not the 100% secondary electron. It might be a contribution from the backscattered electrons also. Okay, so now if this particular scintillator has been switched off, so this plus 12 kV has been switched off, or you can put a small positive voltage. Then what will happen is these secondary electrons are excluded from the detector and only the backscattered electron will be detected. But in this method, what will happen is the backscattered electrons which are traveling towards the scintillator, those only can be detected, because backscattered electrons can travel, it's a high energy, it can travel and in any directions. Okay, so the electrons which are travel towards the scintillator, those can be detected by ET detectors for the backscattered electrons. Now, so that's why for backscattered electrons, the efficiency, the geometrical efficiency is very low by using the ET detector. So for backscattered electron detection, usually we use a scintillator which is called a Robinson detector. Okay, so this Robinson detector, you can see in the schematic, it is kept just above the specimen. Okay, just above the specimen, just below the pole piece. Okay, this is the similar to ET detector, but it is kept at the above the specimen so that you can get maximum number of backscattered electrons which has been collected, can be collected or can be detected. So this has a very high efficiency, this particular Robinson detector. Nowadays, there are also a solid state detectors which are available. These solid state detectors are also kept just below the pole piece above the specimen, but they work on the principle of PN junction silicon. Okay, so it's a semiconductor. So whenever the backscattered electrons hit to the PN junction or with the silicon, then what will happen? It will generate a pair of holes and electrons. And when there is a voltage is applied across the PN junction, then what will happen? It will produce a current. And this produced current can be amplified, and can be detected, which can be core and can be amplified, can be detected, and can be converted to the contrast or the image. So this is how the backscattered electrons are detected by using the solid state detectors. So now we will cover the optics of SEM. So this is the basic thing where there is a filament which produces a beam of electron, or we can call it as a monochromatic beam of electron with a current of I0. Okay, so this is your V, and assume that the size of this particular is D0, fine, or we can call it as a filament dia. Now, if you put up condenser lens of focal length FC, what will happen? Depending upon the focus strength, it will demagnify the image of the filament at position V1, okay, from the condenser lens, and assume that this particular dia is D0, D1, okay, then the D1 can be written as D0 into V1 divided by U1. Here the V1 can be given by the thin lens equation. It can be given by the thin lens equation. Now, if you keep an objective aperture of focal point F0, F objective, the particular beam which is traveling can be further demagnified to a value related to D. Okay, and this D is given by D1 V2 divided by U2. Okay, and here the V2 is nothing but the working distance from the sample surface. So you can write D1 into working distance divided by U2. This is your final probe dia, which will scan across the sample surface. Now, if you need a smaller D size, what should we do? The thing is, here the condenser lens strength controls the beam size. Means the focal, if you increase the condenser lens strength, your FC will reduce. If your FC reduces, then your V1 reduces. That is the distance of that particular spot from the condenser lens. If the V1 reduces, your D1 reduces. And if you see this particular formula, as the D1 reduces, you can see that your D also reduces. So for smaller spot size, actually what we do is we can use the higher condenser lens strength by changing the, but that changes the focal point of that condenser lens. So one more additional thing to be important is the if there is a spherical aberration in the objective lens, then you can actually use the aperture for to reduce the spherical aberration. Okay, so this is the basic thing which the in SEM to control the beam size, especially with the condenser lens strength. Now coming to the pixels, which we describe as a picture element, or we can put as a pixel. What is a picture element? The picture element is, for example, if the minimum size of the spot by the, maybe in the CRT, if it is a 0.1 mm minimum size of the spot or 100 microns, then 100 mm square CRT can produce around 1000 into 1000 pixels. Okay, so size of the pixel is given by P is equals to 100 divided by M micrometers. M is the magnification. This is your pixel size. Now, this pixel size is directly or important for the resolution also. So remember, in earlier class, we described that the resolution is the minimum distance which the two objects can be separated, okay, to resolve A and B. So now, for example, if in your sample, there is a sample feature A and sample feature B, and if you want to resolve A and B, so the resolution should be such that these two should be differentiated. Okay, and to resolve this A and B, most important thing is this A and B should be at the two different pixels. Okay, so the working resolution of any microscope is not no better than the pixel size, which is P. Okay, so if your probe dia D, which is the final probe dia on the sample, is greater than P, for example, here this is the D and each pixel size is P. Here the D is greater than P. What will happen? The signal from the adjacent pixels will also contribute to it, due to which your resolution will degrade. Similarly, if your D is smaller than 1 pixel, then what will happen? You will get a very weak signal per P. And so you will generate a large amount of noise. Right? So the D should be optimum. So D should be equivalent to the pixel size. Then you will get, then you can differentiate the two different objects from the sample surface. Okay. So this is the basics related to your optics of SEM. Okay, now I did not went details into the scanning electron microscopy, so it itself is a complete course. But what I want to bring about this is just to understand that what is a how imaging takes place in the scanning electron microscope. Okay, so in the next slide, what I will describe you is the controlled electron channeling contrast imaging. Okay, now for example, if you have a sample sample with a lattice with a lattice structure, correct? So this is your sample with a lattice structure. Then then parallel electron beam hits to the sample, it will penetrate into the sample surface, correct? So it goes to the into the unit cell or the crystal structure. Now in TEM, what we learned is this unit cell has a certain crystallographic planes, and depending upon the orientation they get diffracted beams, correct? So as in TM we call that if they can get the Bragg diffracted depending upon the orientation, so your electron beam gets diffracted. Once they diffract, there it might possible that they also hit to the crystal, hit to the atoms, and they can get the backscattered electrons. Okay, so in TM, these diffracted beam and the incident beam are collected, so you can get the bright field or the bright contrast. Fine. So this is the principle of TM. Now, if you have a thicker samples, what will happen? These parallel electrons get backscattered. Okay, so they get backscattered, and then these electrons, backscattered electrons, will be detected by the BSC detector, and you will see a dark contrast. Okay, so these backscattered electrons coming from the deep inside the material carrying the information. Okay, so now if there is a presence of defect in the crystal lattice, correct? Now in the left side, the beams which are falling on the crystal lattice, and these are producing the backscattered electrons and detected by backscattering detector. This is called channeling of electron beam. Okay, so now assume that there is a presence of defect, and this parallel electron beam travels across this crystal. Then due to the presence of defect in TEM, what will happen? It gets diffracted. So in bright field image, wherever the defect is present, then those appears as a dark contrast, or those appears as a dark contrast lines, because it gets diffracted from those defect regions. Now in SCM, when it is in the bulk sample, the backscattered electrons due to the presence of defect, the backscattering will increase. If there is an increase in the backscattered increase from those defect locations, then relatively you will get a bright contrast from the defect region as compared to the surrounding dark contrast region, which is due to the backscattered electrons. Okay, so in the presence of defects, the backscattering tendency will increase. So locally there will be an increase in the intensity of the electrons as compared to the surrounding structure. Okay, so you will get a bright contrast lines or the defects in presence of the dark contrast surrounding region. Okay, so this is called electron channeling. So you are channeling the electron and you are getting the contrast imaging of from the defect regions. Here I am showing you two micrographs. These are SCM micrographs taken by the backscatter detector. Okay, and here you can see that we are representing a certain direction G 02 bar 0. What is this 02 bar 0? It means that the crystal is oriented in a two beam condition of 02 bar 0. So it means that there is only a transmitted spot and only a 02 bar 0 diffracted spot. Okay, and which is in this direction. Now it means that you are only allowing 02 bar 0 diffracted beam through the lattice. Correct? It means you are channeling that 02 bar 0 beam, diffracted beam only, and you are actually avoiding all other beams. So this is in the two beam condition. That's why you can see that the surrounding, the whole grain is almost dark. Correct? Now, if there is a presence of defects, correct? So what will happen? These backscattered electrons, what will happen? They will diffracted at these locations very easily, and you will get a higher intensity, due to which you will get a higher intensity at those lines or the dislocation. So you can see these are the dislocation lines. These are the dislocations. Correct? So you are only channeling the 0 2 bar 0 through the lattice, so they get absorbed. But due to the presence of defects, there will be a backscattered electrons generated from those region at a higher intensity relative to the surrounding. So that's why your surrounding appears as a dark. However, at the defect location, these locations are at the bright regions. So here I'm just briefly go through the EBSD. What is EBSD is? This is electron backscattered diffraction. Okay, so here the principle is the sample is tilted at an angle which is usually at a 70 degrees relative to the sample stage, but it is 110 degrees to the BSC detector. Fine. So once the sample is tilted, so this sample tilting is only to elongate the sample volume. As I told you, the signals from the BSC signals will be much higher if your angle is higher, correct? And the electron beam falls on a very small volume on the sample surface. Typically, the spatial resolution is around 20 nanometers. And as these electrons interact with the sample, they get backscattered and they leaves the sample. Okay. Once these backscattered electrons leaves the sample, usually the primary beam loses some of the energy. Correct. And as I told you that if there is these are called inelastic scattering. And when inelastic scattering occurs, it might possible that the electron beam are in the Bragg's condition from the crystallographic planes, specific crystallographic planes. Now, if these are in the crystallographic planes and they are in the Bragg's condition, they can produce the kikuchi lines, which we described in transmission electron microscopy. And these kikuchi lines or the kikuchi bands can be detected by using a EBSD detector near to the sample surface. Okay, so these are very similar, very same as the kikuchi lines which are detected from the in a transmission electron microscope. So here you can see in the right side, you can see these kikuchi bands. This is a particular zone, and remember, as I told you, the thickness of these kikuchi bands are directly corresponds to the d spacing. Okay, corresponds to the d spacing or the G of that particular plane. Correct. So these are the these you can do on the bulk samples to get the crystallographic orientation of that particular grain. So in this there is an example of two grains in a single phase. One grain is at different orientation and another grain is at a different orientation. And if you scan your probe, or if you put your SCM probe at this location, you will get this particular kikuchi pattern, but at this location you will get a different orientation. So you can see that with this you can measure the orientation between these two grains or the orientation of these grains. Okay, so this is a typical unit cell which are oriented as per the kikuchi line, and this is your for the second grain. Okay, so based on this kikuchi patterns, actually you can generate the uh, color maps, and each color corresponds to a particular crystallographic direction. Okay, and these are called IPF maps. And if you see the pole figure, if you then this pole figure is for a cubic structure, usually the low index 111 110. So you can see that 001 111 110 corresponds to different colors. So this corresponds to green, blue and red, green, red, and these are blue. So you can see that this particular sample, most of the grain is textured along 110. So means most of the grains are oriented along 110 direction. Okay, so here you can see that the briefly that how in an electron we can get the electron channeling contrast imaging by channeling the electron, and with the presence of defects you get the backscattered electron intensity higher at those locations, and these also backscattered electrons can be used for the electron backscatter diffraction patterns so that the orientation to get the orientation map. Now I will show you that how this orientation map can be used to get the crystallography of the defects in a bulk sample. Okay, so in this what I will show is um, how to use electron backscatter diffraction to get a proper uh, controlled electron channeling controlled image. Correct. So here there is a cross section where there is an incident beam, there is a specimen chamber, then there is an EBSD detector. Okay, and the specimen is tilted at 70 degrees, and when the electron beam falls on the specimen, then it will generate the backscattered electrons, and as these are inelastically scattered electrons, so they will generate the kikuchi maps, and these kikuchi maps are detected on the EBSD detector. So you will get a kikuchi map and you will get the orientation map of a particular sample. Now if you put a backscattered electron detector, and if you make your sample very near to the backscattered electron detector, and if you arrange your crystal in such a way that it is in two beam condition, such that your the diffracted beam is channeling through the sample surface inside the sample surface. Now at this condition you can actually get the ECP patterns on the BSC detector. Correct. So whatever the backscattered electrons can produce a electron channeling pattern on the BSC detector, which is positioned above the specimen. So, and if you image these electrons, correct? If you image these electrons, you will get a grain where the grain becomes much darker because you are channeling only the one electron beam, correct? So the grain becomes much darker. So based on this principle, what we usually do is first we record the EBSD pattern on a sample surface. So and here you can see that we have selected a region of interest which is in the green color. So the green color corresponds to 110 direction. It's a cubic. It's a cubic pattern. So ROI is 110 direction, and with this orientation, you can get your pole figure of 110, which is a initial orientation of that particular grain. Then this particular orientation can be simulated back into a crystal software, which is a single crystal software, to determine to determine the misorientation angles. Correct. Once these angles are determined by the single crystal software, now it is in the exact zone of 110. Correct. Now what we do is from this pattern you can simulate your kikuchi pattern. So this is your real kikuchi pattern, simulated kikuchi pattern from that particular region, which is a which has a grain which is oriented along near to 110 direction. Now based on the tilting of x or y and the z, correct? Z is the rotation, and in SCMs mostly the tilt is either x or either y, so usually it is x. So based on the x and z, actually you can reorient your kikuchi pattern such that it is in the channeling condition or the Bragg's condition. Once these x and z values are recorded for the two beam condition, those angles can be again used for the sample stage Z movement and sample stage X movement. So you are reorienting your grain to the two beam condition. Now, if you reorient it in the two beam condition, you are channeling that particular diffracted beam. Then when the defects are present in the sample surface, on the sample surface, those get highlighted by the bright regions. So this is the standard pattern for the electron channeling contrast imaging, which is called controlled electron channeling contrast imaging, because you know the orientation of that grain, and based on the orientation, you are actually see the Z and X, getting the Z and X for the two beam condition, and you are putting in the sample stage. Okay, so you can see that steps in the ECCI. First, there is an initial microstructure. You do the EBSD. You are getting the orientation, which is nearly pink color, but it is near to the red. So it is like a near to the red means it is near to the 001. Then you simulate this particular orientation map in a single crystal and get the exact simulated kikuchi pattern from that particular grain oriented. And this particular kikuchi map can be reoriented by Z and the X to get a proper two beam condition. So you can see that in this particular case, this particular beam is in the two beam condition, and you can get the stereographic projection. And these Z and X angles are again incorporated to the into the SEM stage, and you can actually record the ECCI image from that region. Now you can see that large amount of contrast related to the dots, and also at the interfaces you can see the bright contrast, which were absent almost into the initial microstructure. So after going to the two beam condition, you can see that these corresponds to the defect regions, presence of defects in the microstructure. Fine. So these are the steps in the ECCI. Now, ECCI is very useful. You can actually map, or you can quantify the defects in a bulk sample. And as compared to the TM is a very localized information, correct? So ECCI, usually the lateral resolution is around 8 to 10 nanometers. TM, it is 1 to 2 nanometers. Depth of observation is 50 to 100 nanometers. It is 100 to 200. But the observation area is much, much higher than the observation area in the TM samples, which is 4 order of magnitude higher. Then samples can be bulk samples. Here you have to use the thin films. Okay. So this is the difference between TM and ECCI. Now, similarly for the thin foils, you can also do the transmission kikuchi in SEM, which is called transmission kikuchi diffraction. Okay, so this is for the thin foils. So this was first proposed by Keller and Geis in 2012. Usually what you do is you prepare a TM sample, you load on a special holder, correct? And that particular holder is tilted around 38 degrees as compared to the EBSD angle. Then here, then your beam falls onto the sample, and whatever the transmitted beam which is inelastically scattered, these beam inelastically scattered produces a kikuchi map, which can be detected by the EBSD detector. So that's why it is called a transmission EBSD. Here special resolution is very high, down to 2 nanometers. Conventional EBSD is 20 nanometers. Sample is electron transparent here, and these are mounted horizontally and back tilted away from the EBSD detector, and very short working distance of 4 mm. So here the diffraction patterns originate from the bottom surface of the sample and smaller diffraction source volume. So this is your schematically shown, and this is for your shown is for an APT needle, which is an aluminum alloy, where these aluminum alloys are different grains, and these grains can be mapped by the transmission kikuchi diffraction. Okay, so this is a related to your transmission kikuchi. So first we introduced the SCM, then we briefly gone to the electron channeling contrast imaging, then the importance of EBSD orientation map, and how this orientation map and the electron channeling contrast imaging can be used together to get the defect structures on the bulk samples. So these are bulk samples. For the thin foils, anyhow we are doing in the TM, but even in SCM, we can do the transmission EBSD, where the electrons which are transmitted across the sample and these are inelastically scattered, those produces the Kikuchi map on Kikuchi pattern on the EBSD detector and can be used to get the orientation of the particular grain orientation of the particular crystal structure. So here I am giving you a very nice example of a superalloy. So you can see in this that usually these superalloys have a gamma prime and gamma precipitate. So these are the two phase structures, gamma prime and gamma matrix. Okay, so gamma prime is an ordered, gamma is in solid solution. Now these are the creep induced, these are crepe samples. So you can see that this is a SCM image, backscattered image taken in a Zeiss microscope, where you can see that there are certain bright features which are located inside the gamma prime phase. Okay, and these bright features are exactly similar to what we see in TM of stacking faults. Okay, so this particular grain is oriented in two beam Brax condition, and you can see there are four variants of these defects, these fault planes A, B, C, and D. Okay, and you know this orientation of the grain now because it is in the channeling contrast of 002 bar. So you get the stereographic projection, and based on the stereographic projection, actually you can measure the angle of these stacking faults which they are making from the sample surface. Okay, so stacking faults A and D belongs to 1 bar and 1 dislocation planes. 1 bar and 111 planes having an angle of 36 and 38 degrees with the surface plane. So you can measure the angle of the stacking fault from the sample surface. Stacking faults B and C appear as a sharp line which appears that is almost at 80 to 90 degrees from the sample surface. Okay, so and these straight lines corresponds to the stacking faults which usually we'll see in the microscope. Now you have a orientation of that particular grain and stereographic projection is there. So you can actually do the Z and X tilt in the from the software, and you can put these values in your stage so that you can get the different two beam conditions. Okay, so here you can see that that particular region. So usually in these alloys, the displacement vector is 1/3 112, and we can do the similar G dot B or G dot R invisibility criteria as it is can be done in the TM. Fine. So you can see that here in 1 bar 1 condition, your stacking fault B is invisible. Your stacking fault B is invisible. Okay. So these faults are invisible, but in 1 bar 1 condition, your stacking fault C is invisible, and in 2 bar 20, your both A and D gets invisible. Correct? So based on this, you can do the G dot B analysis condition, and you can actually get the nature of stacking faults or nature of stacking faults present in the sample. So this is how we use the ECCI to get the Burgess vector of the dislocations and the displacement vectors for the stacking faults. So as I discussed about SCM, so you are rastering the beam on the sample, correct? And you are getting the information at each at each sample is at each spot interacts with the sample surface and it rasters on the sample surface. Similar to that, we can control the beam in a transmission electron microscope, which is we called as a scanning transmission electron microscope. Okay, so the beam scans parallel to the optic axis at all times so that it mimics the parallel beam in TM even though it's a scanning. Okay, so this is how you can control the beam with the deflection scan coils. Okay, so the STEM image quality depends on the probe size. So there, as I told you, the probe size is between 2 to 10 nanometers. So the probe size here in TM is sub nanometer. Okay, so the probe size is very fine, and you can, there might be aberrations which can be corrected so that your probe size become very sharp so that you can get the atomic resolution imaging also. Okay, so we can use in transmission electron microscope also. Now here, so as you are scanning the beam on a sample surface, okay, and the sample has a different features, okay, and you can see that this is a carbon film and this is a gold sample on the carbon film. So both have a different atomic number. So what will happen when your beam scans on the sample surface? Depending upon the atomic number, actually it can scatter at an angle theta. Higher is the atomic number, higher will be the scattering angle. So it can generate, it can scatter by theta 1, theta 2 or theta 3 depending upon the atomic number. So theta 1 is the highest, greater than 50 milliradians off axis, theta 2 and theta 3. So based on this, what we call is a HADAF, which is a high angle annular dark field detector. Okay, so here what you can see that if your beam, transmitted beam, if your electron beam transmits and if you are putting a bright field detector here, that so which collects the transmitted beam, then that is called a bright field image, bright field STEM image. But if the beam which is get scattered by an angle theta, and if there is a annular dark field detector, because it dark field means the scattered beam is the intensity of the scattered or the diffracted beam is taken for the imaging. These are called annular dark field images. Okay, now if it scatters more than 50 radians, okay, it near to the greater than 50 radians, and this depends upon your atomic number of that particular element, then these are called high angle annular dark field detectors, which is the HADAF image. Here I am showing you an example where this is an aluminum alloy which is having a copper precipitates. Both has a different atomic number. Copper has a higher atomic number. Correct. Now you can see that this is a dark field image. So these are the copper rich plates. Copper rich plates. Aluminum is matrix. So as the beam strikes these copper rich plates, because of the higher atomic number, it will scatter at a higher angle. So what you will do, you will get more signal in the high angle dark field detector. So you will get a higher intensity. So the intensity here scales up with your atomic number. So that's why you can see the contrast between the two regions, aluminum and copper rich regions. Similarly, you can see that there are here three regions, P1, P2 and P3. P2 is related to COAL. These are P1 is related to ammonium rich, CO3 ammonium, and P3 is the matrix. You can see that aluminum has much lower atomic number than the moly and niobium. So that's why the P1, P2 phase becomes much brighter, but the aluminum contrast, you can see that relatively these are darker. Okay, so these are all scales up with your atomic number. Okay, so as I told you, there are if the probe size as the probe size reduces, your resolution also improves. If the probe size is in the order of the lattice near to the lattice spacing, then actually you can get the atomic resolution imaging. However, there are certain aberrations which are very important. Chromatic aberrations, spherical aberrations. Okay, so chromatic aberrations can be avoided by using a monochromator, where you are actually playing with the source. But these astigmatism, uh, spherical aberration, that spherical aberration can be corrected by using several special types of CS correctors. Okay, so these CS correctors are used for the correcting the spherical aberration, so that your probe size becomes almost near to the lattice spacing of any material, so that you can actually get the atomic resolution. Here I am showing you an aluminum alloy. This is your copper rich precipitates. You can see that the bright intensities corresponds to copper rich atomic columns. So this, you are seeing this sample in a particular zone axis, and each spot corresponds to an atomic column. And these bright spots corresponds to a copper rich atomic columns as compared to your aluminum spots. Okay, so with this, I will end this class now. So briefly, I have gone through some basic methods which can be used by using the scanning electron microscope in correlation with transmission electron microscope, and how these can be additionally used with the atom probe tomography. That I will give you a brief example with certain applications related to some structural materials. Okay, in the next class.